In this video, we're going to look at modelling radioactive decay. This is a must-do practical with classes. It's really easy for them to do. They get really good results time after time, and it also nicely visualises the idea of radioactive decay being random. So when we say it's random, what we mean is we can't predict when an individual atom will decay. And we can't alter the rate. It doesn't matter what you do to a radioactive sample. It doesn't matter whether you heat it up, whether you put some force on it. It doesn't matter whether you do a chemical reaction. Nothing will change its rate of decay. It's completely independent of anything you can do to it. But what we can do is model large numbers with statistics. So there's loads of nice links here to modelling other things, modelling biology, modelling populations, in other areas of science. So there's two main ways to do this. We can do it with coins or we can do it with dice. You can also do it with an empty bottle, a full bottle, and if you time how long it takes the water to leave, and you plot the height of the water against the time, you will also get exactly the same graph, and it's exactly the same maths. At school, we tend to use dice. Actually, we've got some yellow cubes that have one face black on them. We've got hundreds of these, but you can also use coins. And the reason either of these work is because we're dealing with exponential decay, where there is a fixed probability of decay in a fixed amount of time. So this definition here, the exponential decay or increase, there's a fixed probability of decay or increase in a fixed amount of time. So a dice and coins, they always have a fixed probability of changing. So what you do is you draw a table of throws versus number of dice or coins remaining. I'm going to start with 14 coins, because that's what I've got at home. You probably want to start ideally with 20 to 30. If you don't have 20 to 30, your graph is not going to look very good. And the larger you have, the better it's going to look. So what you do is you throw them all and you remove any that have heads. Or if it's dice, you would remove any dice that come up a 6 or with the black face pointing up. Weirdly, you need to explain this 2 or 3 times to students, but then they do pick it up quickly. So 1, 2, 3, 4, 5, 6. So throws, 0 throws, I had 14. 1 throw, I've got 6 left. So I'm going to repeat that. I'm going to remove heads. Okay, I've got quite a few heads remaining, so 2 throws, I've only got 2 left. Let's do it again. Oh, and actually this is really quick. It doesn't usually happen quite so quick. Okay, and that's actually one of the nice things, that usually when you get down to 1 or 2, especially with dice, you're actually having to do quite a few rolls remaining, which initially frustrates students, but it really goes to show that there is this fixed probability of decay for an individual atom, and you really cannot predict when an individual atom will decay. So what you're then going to do is you will plot a graph of number of things left, so number of coins remaining, against number of throws. So this will obviously be 1, 2, 3, 4, etc. And this will be starting at whatever I started at, 14, etc. So obviously this graph is not going to give me a particularly good set of results, okay, because it decayed so quickly. But, that's okay. So usually what you'll find when you do this is that the points will be a bit messy. And they'll tend to look something like this. And it's not always immediately obvious that it's a curve, but you really need to stress to students that it is a curve you need to do, and it's a curve of best fit. And you need to tell them that they need to start at the initial value, but then they do a curve of best fit. And the easiest way to draw a curve is usually to actually turn the paper upside down. And then with your hand or with your wrist, if you just move your wrist like this, it will naturally move in a curve. And if they do it in one quick motion by moving their whole hand or whole wrist on the pivot here, they'll get a really nice curve every time. So we're not going to use this one because I just didn't have enough coins, but with dice you will get something like this. So what we can then do is we can work out the half-life of our dice. So whatever our initial number is, we're going to halve it, and we're going to look on the x-axis what this corresponds to. So with a ruler, okay, stress to students that use a ruler. I know this is a really bad example. They're going to draw across and down, and they will come up with a number here. The number is usually between 3 and 4. And then you should say, well, okay, it's great doing it once, but what's always best in science, if we repeat it, take an average. So they're going to halve it again. Okay, they might have a different number to start. It really doesn't matter what you start with, but these are just some numbers for an example. Halve it again. And then they'll probably find it's roughly 7, or it'll be 6 to 8. And then let's do it one more time. So we're going to halve it again, go across, go down, and you'll probably find it's around 10.5 or probably around 9 to 12. And then importantly, what you need to say to students is the half-life, the time it takes, or the number of throws it takes for our dice to halve is this time here. Or, if we're starting here, how long does it take it to halve? Well, it's obviously this distance here. So it's this distance here. Sometimes they go all the way to the start and then here. So now I've got 3 values, and then I can average this and get a good value for my value of half-life. And what is really nice is students don't always know where this is going. And then once you actually start getting results from everyone in the class, they're always going to have something that's pretty similar to this. There might be 1 or 2 that don't. Well, there's probably one group that won't, which is great because you can go, well, that's statistics, isn't there? There's always an outlier. But everyone will have a value similar to this. And then what you can do is you can get a spreadsheet up on the board, and you can do this as students get the results, and you can get a number of groups' results. So here is one group's results from when I last did this, and you can see it's a relatively good curve. Like you could get a fairly nice best fit here. This was with 50 dice, but then what you should do is get 6 or so groups. So when I did this, I think we got the whole class in the end. And I got them to join up with their partners or people next to each other first, and I got every group. So I have 600 in total, which obviously no student is going to sit there and do 600, but you can get the average of everyone's results, and it's completely valid to do it this way. So now we've got a graph, and it's really smooth, okay? And this shows you the power of large numbers. So sometimes I will print this off for students as a comparison with theirs, or I'll just model this on the board, and I will work out the half-life from this. So if I go across some 300 and go down, you'll see it's about here. And again, that's between 3 and 4. If I go from 300 to 150, it's about here, which is about 7 to 8. So it's giving us that nice half-life of between 3 and 4. If you want to go even further, if you've got a really high ability class, you could put on a predicted value. So I've literally modeled a decay of exactly a 6th each time in red.